we're going to do recording first and then share my screen. So right, welcome to today's Advanced R session, the last session of 2021 and of phase one. So next year it will be into phase two, and I know Dan's excited. It's been lots of great project pitch submissions, so fantastic projects to look forward to next year. I'm interested to see how it all turns out. But a last bit of inspiration for how you might like to do things, and just some interesting skills anyway. So today we're going to be covering doing some advanced plotting with the ggplot2 package. Then we're going to look at distributions and distribution fitting, which will be really useful if you're working with distributions in your project, and particularly describing data as a distribution, and creating distributions from your data for when you're using them in things like discrete event simulations and such. So hopefully that'll be a really useful session. And extending that, we're going to go into a bit of web app development with Shiny, and actually look at how in the end we can create a web app that helps facilitate the fitting of distributions for us. So actually the app might be something that you want to take on and extend and use with in your projects if you're doing distribution fitting. So yeah, ggplot2, we're going to look at how to create any graph you can think of. Distribution fitting, describing the shape of your data with probability distributions. And interactive user interfaces for your R code with Shiny. Up on the GitHub repo, hopefully you've all downloaded that already, but you'll see there's quite a few different files and folders for today. The distribution fitting ones are named slightly differently, but it's essentially these, and there's just a whole lot of different examples that we're going to work through today, and kind of not too much hard. I'm not going to be a taskmaster today, basically. It would give you a bit of a rest after the assessment yesterday. So more working through examples, and there's kind of pre-written codes that you can go through, you can explore yourselves and have a bit of a play with. So let's go and jump right in with advanced plotting with ggplot2. So what is this? ggplot2, it is a really powerful plotting library. And it was developed based on this, what's called this kind of aesthetic language. It's termed the grammar of graphics. And this makes it a bit more complex than using base plotting functions, but actually it also makes it extremely flexible. And it means that you can layer up and create graphs on graphs and mash them together in different ways to display your data in the way that you want to. And they do look nice as well. Yeah, the matplotlib library that is used in Python is actually based on a combination of MATLAB, that's the one that I was trying to think of MATLAB, and ggplot2's plotting style. So it's kind of a combination of the two. So if you've ever used, you'll see some of the similarities between the style of plot that's output. And there are entire books on ggplot2 if you are so interested, because yeah, there's that much that you can do with it. But today we're going to get an overview of it. So let's look at the basic ggplot components. So you use these different components to build up your plot. So we get the actual plot object itself, and it's to the plot object that we can attach lots of different things. So we can add in geometry layers, and the geometry layers, we'll go into this in a bit more detail in a bit, but yeah, these are essentially, these are your points or your lines, your different actual bits of plot that you want to put on the graph. Then we're bringing in this kind of the aesthetical language, and it does aesthetic mapping to your plot layers. So we get these aesthetics layers as well. And then we get specific label options that we can attach to the plot object. And then something called faceting specifications. And this is to do with how the multiple plots can be laid out. Then we get coordinate systems. So we can change the coordinate system of the plot by calling this these coordinate system functions that are part of the ggplot object, and attaching them to it. So when we start building up a plot, we can we start very simply with the ggplot object. That's the very first thing that needs to go in, and normally that's where you're going to attach your data set to. And this is your data frame that has all your contains all of your data in, that you can reference then later on in the rest of the plot objects. When we're adding different elements to the ggplot object, we use the plus operator to say, okay, this is then going to be included as well in my plot object. So we use a series of plus operators to keep adding things to the object. And then we can call any of the other components and functions and add the different mappings to our plot object. So normally you'd call, in the most simple terms, call a geometry function and then do some aesthetic mapping on that. And we'll see examples of this. So yeah, let's start having a look at some examples. So there's some built-in data that makes it nice and simple to do some examples with ggplot2. And this is a data set called MPG. And what we're going to do is we're going to assign the data to the ggplot object, and then add a geometry layer and tell it which are the X and the Y coordinate variables. And here we can see in these two lines of code here that we have the ggplot object with MPG attached as the data. And then we've got our plus operator to say we're going to add another layer to this, and it's going to be a point geometry layer. So we're creating a scatter plot here. And then within the mapping, we're going to add as the aesthetics to tell it which columns in the MPG data set represent the X and the Y of our scatter plot. So I'm just going to switch over to R now, and I will zoom in for you. So here in my code, and you can either copy along or just watch, depending on what's easiest for you. So this ggplot code has also been included in the GitHub repo. So you've got this here as a reference. So we first import the ggplot2 library, always where we start with these things. And then we can bring in the MPG dataset. And here, this is a data frame. It has 234 observations of 11 variables. And if we have a quick look at this, basically, as MPG might indicate, miles per gallon, this is all about fuel efficiency of cars. And so we get manufacturer of the car, model of car, the displacement, which represents the engine size. So a 1.8 litre, a 2 litre, 2.8 litre car. Then the year that it was built, the number of cylinders that it has, the type of transmission, so automatic or manual, the drive type, which is front wheel drive, rear wheel drive, or four wheel drive. Then you've got the fuel efficiency, which is CTY representing city driving, and then HWY representing the fuel efficiency on highways. Then we have the FL. What does FL stand for? I've forgotten that one. I don't think we use it. It's all right. Forget what FL means. It might be fuel type. No, not sure what that stands for. I can find out though. And then the class of the car, which is here we got compacts, mid-size, SUVs. It's an American data set, so the terminology is such. But it gives us a few different options here to be able to explore the functionality of ggplot. So here we've got our this first line of code that I showed you on the slide. And this is the ggplot object, bringing in data as MPG, and the point geometry layer, and mapping the aesthetics. So we're mapping displacement on X, which is the engine size, and then Y to the Y-axis, mapping the highway fuel efficiency. So in that way, we can see, given relative to engine size, what is the fuel efficiency of these cars on the highway. So you'll notice here that I've highlighted these two rows, these two lines in the code, and I'm going to run them together as they run. It's easier to run them as a block rather than running it individually line by line. Sometimes it can get confused and not produce the plot. So here I've created the plot, and we can start to see the trend here that we've got as engine size increases, highway fuel efficiency seems to generally, as a general trend, decrease, which makes sense. So this is the type of output that you get from ggplot2. Is a nicely formatted graph that has major grid lines on it in the background, which are useful just for being able to go across on your graph. And those are things that you can change as well. I believe make mention of the grid lines later on. And it just is, it's a nice graph display format. So it is that easy to create a scatter graph with ggplot2. So just, you know, it's remembering to bring your data set in as in the plot object, then in your layer, in your geometry layer, you are mapping to the aesthetics the columns that are being used for displacement, that are being used on the X and the Y axis. We can go further with the aesthetics arguments and use them to change other facets of the plot itself. So some examples of these are, we can change the color of the points or the lines if we're using a line geometry layer. We can change the size of the points in the scatter plot. We can change the alpha, which refers to the opacity, so how well saturated the color is, and the shape of the points as well. So we can see a couple of examples of that here. So if I run this next example here, we can see that within aesthetics, we've used the keyword color, and we coloring by class. So this is not giving a direct color. What we want to do is split these by class. And if we look back at the data, saying that class is the type of vehicle here. So it will take a variable and then treating this as a categorical variable, attribute colors to the different categories. So if we run this now, let's get the right one. Here we are. So we can see that we have the same two things plotted on our X and Y axis, but this time the dots are colored by class, and it's nicely created a nicely formatted legend here on the right hand side. We can also do this with, so we can use change the size of the points. And again, we have a legend created for us, and this is, so it's created gradated sizes across. This is actually, if you remember from the network analysis session, we're talking about linear interpolation. This is another example of this, but with size. So across a gradient, it's selected equal steps of size for the points and then attributed them to the different categories. So here, so interestingly, this is where you're using a, so it's continuous interpolation, because the gradient could be used with a continuous variable, and we could have, it could be, rather than discrete categories, it could be continuous numbers. And so instead of that, it's just use equal steps for these discrete categories, but on a continuous attribute of the size of the points. An example with alpha is that, again, we've got the opacity of the different categories across, which are equal steps across a linear gradient. And interestingly, if you look down here at the console, it's actually throwing a warning message saying using alpha for a discrete variable is not advised. So this comes back to this idea of different types of aesthetic display are more or less appropriate for particular, whether continuous or discrete variables. And it's just useful to bear that in mind. And so looking at what was discussed in the advanced network analysis session in the visualization, that gives a breakdown of whether you should be using discrete or continuous aesthetic attributes for discrete or continuous variables. If we use shape now, we actually get, again, this one doesn't throw the warning for saying, oh, there's, this, you shouldn't use this discrete variable for a continuous attribute. But instead, it's thrown another warning message here, just saying that the shape palette can deal with a maximum of 6 discrete values, because more than 6 becomes difficult to discriminate and you have 7. So here it says, consider specifying shapes manually if you must have them, so that you can get that real definition. And that's really helpful, actually. That's incredibly good advice. Having too many discrete categories can make things incredibly confusing on a graph. And ggplot2 has just been very helpful there. So just going to, because that goes on to labels, right? If we are looking to just set all of the points to the same color, where we put the color keyword in the geometry layer is actually outside of the aesthetics mapping. So instead of mapping to individual points, we are mapping to, we're actually setting the color for all of the points as a whole. So it goes outside of the mapping keyword and outside of the aesthetics, and just can be directly entered into the geometry layer itself. So we're going to set the color of the points to blue, and that just changes all of our points in the graph to blue. There are lots of little quirks in ggplot, which hopefully I've tried to pick up on a lot of them, and try to give a little bit of this overview of this language of graphics, and to hopefully kind of give a bit of a reference to what something that you can come back to go, oh, where should that actually go in the syntax itself, in the arguments? Okay, so we've got a nice plot now. It can change the point colors, we can change the size of them, and so our scatter plot geometry and aesthetics, you know, it looks all right. But it was just taking the column names as the X and Y axis labels. So using DISPL and HWY, the shortened column names as the axis labels. When we want to add the axis, name any labels, do any labeling, we add that as a separate component, a labels component. And again, we use the plus operator to add another layer. And the labs argument is then followed by the keyword arguments for the different labels that we want to use. So here we have the title and X and Y axis labels, which is all nice and self-explanatory. So if I just come out, and so I've got the code here that's running this again as a block, just much easier. And data going in, we're still doing our geometry layer and mapping what goes on the X and the Y axis, setting the color of the points, and then changing the title for the plot overall and the X and Y labels in the labels component. So then we can see in this plot now, it's all been changed. So that's labels. They work that simply. Right, now, facet wrapping. It's an incredibly nondescript term to use, I think. It's not something that immediately that you go to, oh, facet wrapping. Oh, that's how I'm actually laying my graphs out. It's not that intuitive, but yeah, this is how the plots are split up and organized. And for example, we can split our graph out and do it by a particular facet. I suppose this is where it makes more sense, that we can create multiple graphs instead of having them all in one graph, and we can do this for a categorical variable here by class is a nice simple one. And so it's using the somebody else might know what this is called, the squiggle. I call it the squiggle. The squiggle operator, a space, and then the column name that we're using here, which is in this instance class of vehicle. And so that's our first argument in the facet wrap layer, in the facet wrap component, to say, okay, I want to split my graphs up by class, and I would like them displayed in 2 rows. So if I now run this facet wrap function for you. So yeah, here we're bringing in our data. We're then adding the point geometry layer and mapping in our aesthetics displacement to X and highway efficiency to Y again. And then we're adding another layer using the plus operator. And this is our facet wrap. And this is, so by class is what this means. The tilde, that's what it's called. Remembered. And so the tilde or squiggle is used as the, I want you to do this by something. So by class in 2 rows, lay out my graphs, please. And here we find that we have 7 different categories. And we have 2 rows of graph for our different classes. And ggplot very helpfully provides the name of each class at the top of the subgraph itself. And the way that it's sorted out our X and Y axes is each individual graph has its own little X and Y axis, but rather than messing about doing labeling for each individual subplot, it's just labeling the X and Y axes just once for us. Now, we can also go on to do to split our graph up by multiple different factors. So here we're going to create a grid where we're doing the drive type, which is front wheel drive, rear wheel drive, and 4-wheel drive type, and by the number of cylinders that that particular vehicle has. So when we run this, it produces for us a grid of plots showing that we have here along the top the number of cylinders, 4 cylinders, 5 cylinders, 6 and 8. And then down the y-axis side, we've got 4-wheel drive, front-wheel drive, and rear-wheel drive. So this essentially, we're saying I would like to know, drive type by the number of cylinders. Plot those graphs for me. This saves any need to manually subset your graphs and your data. It will do it automatically for you. This can be really, really handy, really powerful way to create quick subplots of your data across multiple different categories. Okay, yeah, and this is what we're just saying. So yeah, plotting by 2 says reference in here to this, that you can plot by 2 variables, enabling easy comparison, and that's facet grid for you. And it's just remembering that the 2 variables are split by the tilde operator here. Right, there are lots of different geometry layers, and I've provided a link to the documentation here for the ggplot2 and an overview of the layer types. This is also repeated in, and I'll show you this now, within the GitHub repo, you will see that there is a ggplot2 notes. This contains references, all the links, and all of the references, all of the code, just kind of laid out and given just to help along the way. So it can act as a bit of a cheat sheet for ggplot2 if that's helpful. In fact, it's worth mentioning here in the aesthetics, these are the, if you want to set shapes manually, the shapes of the points, these are the codes that are used for setting them. Okay, and there is also a second document, which is the geometry layer functions cheat sheet as well. And this basically, I've distilled down what is in the ggplot2 documentation and given you the kind of the basics for the different geometry layers that can be used in a ggplot2 graph, and kind of hopefully the basic necessary information. So we start seeing here that we have some graphical primitives. So and there's little descriptions next to each of these. So we've been using geometry point at the moment, so plotting points for a scatter plot. But we have bar charts, we have histograms, density plots, frequency polyplots. We have smooth, which we'll look at in a minute, for line plots. There are violin plots in here, box plots, area plots. There's a whole vast range of different types of graph and different types of layer, so geometric layer that you can build up. And this is where ggplot2 becomes a bit more complicated than your standard base plotting library, because it gives this huge level of flexibility in being able to use these multiple layers and build them up in a way that you want. But you've got to play about and kind of know how to use them. And there are loads and loads of examples online, and this is why there's books on it, because it's how to use these different layers in combination to create useful and useful graphs for different types of data. So let's next look at adding multiple layers to our graph. Why not? Let's, so here, what we're going to do is we're going to, again, add our points. So I create a scatter plot. And it's going to be, we're going to use displacement and highway efficiency again. But this time, color them by the drive, color the points by the drive type. So front wheel drive, rear wheel drive, and four wheel drive. Then using the plus operator again, we're going to add another geometry layer. And this time it's going to be smooth. So as you'll see, geometry, a smooth geometry refers to a smooth line through the points. And here again, we're going to say we're going to be mapping to our aesthetics that it's going to be displacement by highway efficiency, but this time using the line type argument to say I want you to change the line type and create separate lines by the drive type. Let's see what that looks like. So here, let's build this up gradually and see this more individually. Here's an example just of the smooth line. And this is for just doing, basically plotting a smooth line through our through the points. So it's using interpolation, essentially creating a regression line through our points with an error with an error bar on it as well, error shading. So if we introduce drive type now as a way of classifying our X and Y data, here we get 3 separate lines for those vehicles that are 4-wheel drive, front-wheel drive, and rear-wheel drive. And you can see that it's created different line types for this and plotted a line through the points, and then given the error here as well of the interpolated regression line. We can then bring that together, bring these 2 plots together in terms of having our scatter plot. So we can see here that front-wheel drive is those that are green dots and this dash, small dashed line. And we can see how that fits through the middle of the points using that interpolation. And then for 4-wheel drive down here, see the same. And you notice here with the error bars that where the spread of the data is less, they're much closer in towards the line. That's just is showing that spread and the error of the interpolation. So one thing that ggplot2 interestingly does here is that it integrates into the legend the 2 different it's recognized that we use in the same category, so it can show them in the same item on the legend, both the line type for the smooth geometry layer and the point color for the point geometry layer. And that's just a nice little quirk that helps keep the graph tidy, you know, and shows kind of the power of these very specifically targeted packages. It doesn't do this on the base plotting functions. So here, with only 3 lines of code, we're building up what is actually quite a complex graph now. And it's by using these different layers in combination that we can create increasingly useful and hopefully not too complex, but interpretable graphs. Okay. Global mapping. Now, this is, it sounds very grand, but this is to do with the the aesthetics mapping that we have for our plots. So here, in the last example, we twice defined what the X and the Y columns, Y-axes are representing, what data to place on them. And in both instances, it was the same, that we're using displacement on the X and highway efficiency on the Y-axis. And so this is just reproduction of effort. We can use global mapping by mapping to the ggplot object to say, globally, across my plot here, I would like you to map to the x-axis displacement and to the y-axis highway efficiency. Then when we add our point and smooth geometry layers, we no longer have to give that X and Y mapping. We can just focus on giving the color and line type keyword arguments. And so this, when this is run, produces exactly the same graph, and it just reduces the amount of code that you have to write. But it's this concept of what is given in the ggplot object itself is globally applied to the relevant layers below in the rest of the plot. And you can override that global mapping at any time by then giving an alternative X and Y, or whatever mapping is given globally in the individual layers themselves. So it's just this trying to understand how exactly these ggplot is ordering the hierarchy of its aesthetics mappings. Global trumps, global will be passed on to the other layers, but the other layers can override the global options if needed. Right. So bar plots are a really handy way to organize your data. And within a bar plot, we use bar plots are used all the time. Great way to organize your data. And they organize it into something called bins. And both bar plots and histograms in ggplot2 use this kind of bin idea. And here we're splitting them into bins by a particular variable, and that is by class. And so using a bar geometry layer, we're mapping in the aesthetics that on the x-axis, what we would like to bin our data by the category class. And when we do this, you can see that a bar chart is created using the 7 different categories of vehicle that we have in the data, and producing the frequency count up on the y-axis. And again, you can go in and you can do all the coloring for the different bars by using the color keyword as well. Okay. Statistical transformations. Now, this is something we haven't mentioned yet. ggplot2 has some built-in ability to do some statistical transformations on your data and produce new outputs that can be used in the plot itself. Now, I'll put my hands up here and say this is not something that I've played around a lot with, but it's something that I wanted to make sure that you're aware of, because it could be, if you get into using R more regularly, this can be quite useful. So instead of having to create separate variables outside of your plot, you can create them. You can create statistical variables in the plot itself. So if we look at the example of stat count here, ooh, is that going to do anything? No. This is why I haven't played around with it a lot. I will come back with an example after later on around that. That didn't quite work as I expected it to. Okay, we'll skip over the statistical transformations for a moment, as that did not work as I expected it to. Coordinates. Let's talk about coordinates instead. So we can transform the coordinates of our coordinate types of our plots as well. So again, this gets onto really advanced use of ggplot2, because you need to be looking at other examples of where people have done this before, or playing about with it yourself, to see how these different coordinate systems affect different geometry layers, is the one here. So here, what we're going to do is create a box plot, and then we're going to flip the coordinates of the box plot. And these should, fingers crossed, here we have our box plot. And for our different, for class against highway efficiency. So we've got the classes of vehicle, and then we're looking at the spread and the average, quartile, interquartile range, and spread and outliers, as shown in the box plot, for those different categories with their highway efficiency. Now, if we do a coordinate flip, this should turn it the other way around. Oh, I'm glad it did that. So here we can just change from a vertical to a horizontal box plot. And here, also given, oh no, we'll come back to that in a moment. So we can play about with our coordinates, and we can create all these different graphs with all these different layers and all these different aesthetic mappings, but it's always handy to be able to save the plots. So ggplot2 has a specific save function, which is ggsave, and this I find produces a slightly higher quality plot when it's output than using the export. You can still do direct export of the plot from here, but it's also just programmatically that you can also save your plot using ggSave here, and you specify the name of the plot, including the file extension, which normally is just best to use. You can use ping, and then you then say what plot it is that you want to save. And here we're going to create this plot called bar and then save that as an output. So here, the bar plot that we're going to create is attaching the MPG data, then adding a bar geometry layer and mapping to that class. And we're going to do the fill color of the bars by class. So each class will have a different color. Not going to show a legend with this as it's unnecessary. All of the categories of class will be given on the x-axis. And we're going to set the width of the bars as well to 1. Then, in addition to the bar geometry layer, we're going to use theme, and this sets some overall parameters for the plot itself. And here, these are kind of the overall visual parameters for the plot space are set in theme. And here is using aspect ratio and setting that as 1. So it maintains a 1-to-1 aspect. It should maintain a 1-to-1 aspect ratio. And then we're going to say that we don't want any X and Y labels. We're going to flip the bar coordinates to horizontal and then transform it into polar coordinates. And let's have a look at this. So here we have what is now on the y-axis, the different categories of car. On the x-axis, we've got our frequency count, and then it's being filled by the class type. We've got no legend being shown. We're in a 1-to-1 aspect ratio for the plot itself. And we don't have any X and Y labels. Now, if I transform the coordinates to polar, here we get a plot that is a polar coordinate plot. And just out of interest, that being able to this is kind of the interesting power again of ggplot2, that you can transform a bar plot directly into a plot of polar coordinates just by giving the transformation component to your bar plot. And yeah, here what we see is that we still have count, but count is relative to the to how far out on these polar coordinates it is they are extending. Just a different way to be able to present your data, and it might be relevant in some situations. Okay. Just one last example that I thought I'd throw in, as I don't think this is included in the slides, just showing a histogram, as well as we create lots of histograms, and it's always useful to be able to do them. So ggplot2 has a specific histogram layer, and here we can set we're setting that we want to create a histogram of highway fuel efficiency, and that we're going to set the color of the histogram bars to black. No, hang on, let's just see which way around this is. Oh, so the outline color sorry, the outline color of the bars is set to black using the col argument, and fill is used to set the color of the bars themselves to gray. Now, there is all of this information is contained, and it is, if you're going to do work with ggplot2, you will want to work with the documentation until you get used to it. This is kind of an overview, but you really will want to get stuck in, as there's a lot of different arguments that can be used, and the documentation is fantastic. It goes through and it explains all of the different arguments that you can use for each different component and function layer at each different layer. Gives lots of examples as well. Highly recommend going through and having a look at this. So yeah, just to say, there's lots on there, and we can see examples here of how to create things, file in plots. It's interesting random walk between points plot there. And yeah, there's yeah, I'll have a little look at stats bit, as I probably should have looked at that again before this session. Okay. So just giving a bit of a final kind of generic overview of how the structure of the graphical grammar tends to work, is that we start with our ggplot object and assign our main data set to it. That's common across all GG2 plots. Then we're always using the plus operator to add a new layer, and normally the second layer or component that you'd add is the geometry function. Within the geometry function, you give the mapping and provide the aesthetics mappings. So these are all the different keywords for the aesthetics, and quite often we're defining what in the layer is on the X or X axis, or on the X and Y axes, and any particular class-based or any particular category-based color mappings or different mappings that we want to do to the geometry layer itself, if it is by category or by scaled value along across a color map. Within the geometry function, we also give any stats transformations that want to be passed to it. And again, I'll find a decent bit of documentation on that for you. And then we also pass any position parameters, as we can go in and specifically change the position of things within the geometry layer itself. Then the next component that you're normally changing would be the coordinates function, any coordinate transformations that you want to perform, and then any facet functions that you might want to use. So if you're creating subplots there, you're looking at things by facet. So on my random walkthrough ggplot2 there, hope it's given you enough of an introduction to go in and have a play with another data set. And this is, again, it's a built-in ggplot2 data set, just for ease here. And you call this data set by using this syntax here, ggplot2 : Midwest. And what I'd like you to do, let's just have a look at the time. Yeah, what I'd like you to do is to go in and, using the Midwest data set, create a couple of graphs using ggplot2 and come back and, well, let's say put your graphs up on Slack and pop them in the module 1 channel so everybody can see them, and we can all go in and have a look at the interesting graphs that you have created around this data set. If we take half an hour for this, I'm going to put you into breakout groups in a moment. If you take half an hour, so we'll come back together at 11:10. And if during that time you take a 10-minute comfort break as well, but just do it between yourselves, whether you'd like to take a comfort break now or just before or at 11 o'clock when you come back, or whenever in between, and have a go at creating 1 or 2 graphs showing something interesting about the Midwest data set, just for fun. And just to have a play at writing your own graph functions here. As I say, you've got the notes and the layer function references. So just have a go at, do make use of them. There's far too much about ggplot2 for me to tell you in an hour-and-a-half session. So yeah, start simple, build it up, find out what the additional keyword arguments that you can use for the different layers, and have a play. I will now pop you into your stop sharing. Oh, is it going to stop share? Is it frozen? Oh dear. Apparently I can't stop sharing. Okay, I'm going to open the breakout rooms. So, did anybody manage to create any graphs? Are any graphs going up in the on the Slack channel? I can see one. We've got one. Excellent. Thank you, Sally. So there we got the percentage of American Indians and whether they're below the poverty line by state. It's a nice way of splitting out and using the different variables there while colouring based on state. Nicely done. Hopefully everybody had a bit of an opportunity to try and produce a graph. If you have produced one and would like to put it up on in the module 1 Slack channel, that'd be great. Let everybody see what you've managed to produce. Even a little note there that did a bit of a data cleaning on there. That was an outlier state that was cut off. Little bit of managing the data. Nicely done. Okay. Oh, we got another scatter plot come in from Andy here. So here, making use of both color in terms of for two different variables, so the population total and the in metro variable. So I'm assuming in metropolitan areas, perhaps. And then we got the population density and percentage white. And we can see some quite clear trends coming out there, but nice use of with the population total there as well. Yeah, nice example of building up the different layers there and using the different aesthetics to embed multiple different pieces of information within the graph. Excellent. So I did mention as well that I would find so a little bit of information around stat. I think stat's been updated since I last looked at it, and some of the stat functions have been changed within ggplot2 in the latest versions, and they've kind of used it for some more complex stat functions, so cumulative distributions, drawing functions as continuous curves. Yeah, actually something I probably won't cover next year. But if it is something that you're interested in, do have a look. This is the ggplot2 reference material here, which has all of the different functions, and you can go in and look at the different functions in greater detail. So understanding what goes into the different arguments in the different layers, and how to construct them and use them with examples in ggplot2. So if you do find yourself going, oh, I'd really like to use ggplot2, this is your Bible, and have a good look around that. And the links to these resources are all in the slides themselves as well. So the next thing that we're going to talk today, after that very brief adjourn through ggplot2, is working with distributions. And so this, we're going to go into a little bit of detail about what distributions are and how to use them, when to use them, and producing them in R. And this is because I think quite a few of you will, in your projects, be looking at using distributions, so it's worth having a good look at them. So what is a distribution? At its highest level, a distribution is a description of the shape of some data. It's all about understanding what is the actual probability model of the probability of a particular value occurring in that data set. And it's the probability of the particular value occurring that we're really interested in. That's the shape. That's the particular shape that we're looking at. And it enables us to give this concise mathematical description of a curve that fits the spread of the potential values. So here we're really including information about the variance within the data, so that we can capture this stochasticity that exists in real data sets. So we get some raw data, and this is just a scatter plot of some data. And here, when we're looking at this, we can see that a lot of the values sit towards this bottom end of the y-axis. There's greater density of points down here, and it lessens the higher that the values go. And when we look at this, we can start to see a bit of a pattern in the data, in that we have more values lower down and less higher up. But this doesn't help us with putting numbers to the probabilities as yet. But this is normally the first type of view that you'll end up taking of your data. You plot it like this. But then the next kind of view that we want to look at of our data really is a histogram. And a histogram starts telling us how many different values lie within different ranges. So what we have here is a histogram, again, of this same data set. And we can see for different ranges of values, so these are the bins are ranges of values along the x-axis, and the number of values that fall into that particular range are counted on the y-axis. And this starts to give us a bit more of an idea of the shape of our data, that we can see there's more down the bottom as we saw in the scatter plot, but we can start to quantify how many values sit in that lower range, and then in the different ranges as we go up. This also starts to give us an indication of the type of skew on the data, that this data will be negatively skewed towards 0, and that this is what this is one of the types of measures that we use for describing the shape of data. We also get something called the probability density function. Now, the probability density function is based on the histogram, and it is a smooth curve that describes the probability of a value occurring within a particular range. And that's that dashed line that we can see here. And this will become important because this is used within our the probability density function is used within some of the distribution fitting calculations. Then we get something that's called the cumulative density function. Now, this is basically transforming the PDF, the probability density function, and adding those probabilities up to produce this increasing curve. And this is adding all of those individual probabilities calculated in the probability density function up, so that we can see how quickly it gives us a different view of these, how the probabilities are changing across the distribution. So we can see that there are more values within this probability range, down low here towards the lower end of our data values, and then it tails off starting around kind of 25, value of 25 in our data, and there's a lot less values. The probability of a value being over 25 is much less. So it's just a couple of different ways of looking at the data there, and how it starts to starts to calculate the probability of different values occurring within our data set. So there are two main types of groups of distributions. These are discrete distributions and continuous distributions. Now, discrete distributions are where we're using discrete values. So this is where you don't have continuous numbers. You don't have decimal points after your numbers. So either you're working with the probability of categorical variables occurring, or you're working with purely there's no decimal points, although there's a funny bit of a crossover between discrete and continuous distributions, that if you can use continuous distributions with data that doesn't have a decimal point as well. So just a bit of a funny crossover. So the different types of discrete name distribution are the uniform distribution, which is where every value in the distribution has the same probability of occurring. The Bernoulli distribution, which can be used for dictonomous variables where there's only two options. So these are used in looking at things like yes and no types of answers, or whether it's just where there's only a very limited set of options, normally two with Bernoulli. Then we get the binomial distribution, which is one that you might well remember from maths at school. And this is similar to the Poisson distribution. However, the binomial distribution tends to be used with categorical variables, but with multiple categories. And the Poisson distribution tends to be used with data that is on that cusp between continuous and discrete, where they are integer values. And that's the main difference between the binomial and the Poisson. I've got to say, everything that I'm telling you with this distribution fitting is rule of thumb. And we'll see as we go through that this is a real art form, and there are no hard and fast rules with distribution fitting. It's all quite flexible. So the other discrete distribution to mention is the geometric distribution, which fits more what is similar to exponential data. And this is used when for the discrete variables, where you tend to have more of a slope rather than a hill type distribution. For continuous distributions, there's a number of, and this is by no means the complete list of named distributions, for there are many, but these are the most commonly used named distributions, and those are most easily implemented in R and also Python. So continuous distributions, we have things like the exponential distribution, which is a smooth curve, described as a smooth curve. This is a negative exponential distribution, and if the curve goes up the other way, it's a positive exponential distribution. Then we get distributions such as Weibull, which is, in fact, actually, it's easier if I start on the normal. Most people know what the normal or Gaussian distribution is. This is where we have symmetry around the mean of the distribution. And if kind of A-level statistics, you'll often be working with the normal distribution. So it might be one that you're familiar with. And yeah, so this relies on the mean being in the middle of the data and it being symmetrical about the mean. The student's t-test is a squeezed version of the normal distribution, which sits closer around the mean, and came about as a result of lots of psychology experiments assuming the mean. I wouldn't really worry about that. The log normal distribution is a bit of a mix between the exponential and the normal distribution, in that it is skewed, is negatively skewed, so down towards 0, and represents more of a logarithmic scale. It still has a hill climb, but that happens very steeply in the data. The log normal distribution is an important one to know about, as it's commonly used in, it commonly crops up in healthcare data, and it often represents things like inter-arrival times and lengths of stay are often described by a log normal distribution rather than a normal distribution. We don't tend to see the normal shape for those kind of factors within our models. The chi-squared distribution is an exaggerated log normal kind of shape, and again can be useful, as is the gamma distribution. And then the beta distribution is a mirror of the gamma distribution. It's almost a mirror. And the Weibull distribution is a skewed version of the normal distribution. So what we see here is that it's all about this shape of the data that we're trying to describe. And these different named distributions describe fairly generic shapes. And we can squish and change or pull these slightly and tweak them about using different parameters of their mathematical description to try and get them to fit our data. And that's the whole game with distribution fitting, is to see which named distribution can be squeezed and manipulated to estimate our data, our real world data. And then we can use that distribution's description to describe our data. So kind of very generalized common uses of distributions are for inferential statistics, commonly used for hypothesis testing. For example, lots of you might have used things like t-test. So the t-test assumes a normal distribution, and it is what we're looking for when we do a t-test is we're looking at the difference between the means and then the standard deviations, and whether we have an overlap in the standard deviation from the mean within the distributions. Now, an interesting thing here is that a lot of healthcare data doesn't fit a normal distribution, and actually t-tests are not often the most useful way to look at healthcare data unless you do transformations on it to transform it into a normal distribution. So we're conducting t-tests to look at statistical significance between samples. We actually need to get that assumption of normality correct. So distributions play this real role in where we're doing statistical testing, and so it's really important to understand these underlying distributions that are being used when we're doing hypothesis testing and testing for significant statistical differences. We also use them for determining uncertainty, as it's the shape of the distribution itself and the variance that enables us to understand uncertainty around the mean. And it is the probability distribution that determines the standard deviation within when you're looking at your data. The predictive modeling. So this is what predominantly you've been learning about during the HSMA, or one of the core things. So we use distributions all the time for parameterizing models. And so you'd have done this with the discrete event training. So there you were using distributions to set things like your inter-arrival rates, your activity times, and it's that probability, the probabilistic model that enables us to have that variance, stochasticity, and capturing that variation that we see in the real world and being able to embed that into a model. And it's also really useful for data engineering. Imputing missing data using probability distributions is a great way to be able to fill in missing data and complete data better. So we can create a probability distribution of our data and then select values from that in order to complete our data. So in the real world, distributions are commonly used for things like manufacturing process control, where you'd be looking at the distribution of timings of activities through a system. This is one of the main places where discrete event simulation was developed. And they look at deviation from, to see that the mean in the manufacturing process, the time that it's taking to do particular tasks is not varying. This is the basis for statistical process control. We get things like workflow planning to understand what the variation within a system might be and how long tasks could take, and build contingencies. Probability distributions are used heavily in robotics. They actually use them so for movement in robots, they don't have discrete factors such as taking an input and saying, I must place my foot here. There's a probability distribution built around the movement of any part of a robot. And they actually use noisy interference between different components and fuzzy logic. It all gets very complicated, but they're basically using multiple probability distributions to across different components of a robot and adding them all up to say that you should probably move here and move in this way. And that way it works much better than a fixed discrete choice of arm opening, arm closing. So arm moving slightly more, leg moving slightly more up, slightly more down. It's all built around probability distributions. Your insurance is worked out based on probability distributions. So insurance companies build these probabilistic models in which they put a load of variables in about you. So your age, gender, where you live, your profession, all these different bits that they ask you when you're completing your insurance forms, and they all go into a series of probability distributions, which are all cross-correlated, and they look at what is the likelihood that you will make a claim on your insurance based on those parameters. And that's how they generate your insurance quotes. And health service modeling. We use these all the time. And in terms of just describing a data set. It's much more useful to use a probability distribution than it is to use simple descriptive statistics. Okay, so in health service modelling, as I've already mentioned, we use these to determine things like inter-arrival times, so to an emergency department, to a GP's clinic. We take the real-world data for the inter-arrival times and then describe the distribution of them. Determining how long an activity will take is an important one because they don't take fixed amounts of time normally. Something that takes somebody 5 minutes might take somebody else 10 minutes, or it's just that particular task on a particular day just happens to take a bit longer. But collecting all of those different activity times will enable you to understand how often can it take. Attributing characteristics to individuals is a really interesting use here. So in a model, we're often creating, we're not using real world data as such. We are creating distributions of it for our inter-arrival times, for activity times. But if we want to give characteristics to individuals, we might see that we've got 30% males in our sample and 70% female. But that might not be static, or we might want to use something like a Bernoulli distribution to say, okay, I want you to choose when to give this attribute 30% of the time to males, 70% females, and you can use that rather than having to pre-allocate 30% males, 70% females, for example. And these can be cross-correlated with age. So you could have different Bernoulli male-female distributions for different age groups, for example. And so you could allocate age based on the distribution of age, and then allocate gender based on the age of the individual. Simply determine the probability of an event occurring. So, for example, you might have different routing through your model, and we can determine whether somebody should take path A, path B, or path C based on the probability of such routing, or whether they require treatment, don't require treatment. Those can all be built again on probability distributions. And likewise, we can use it for particular treatment being given or a particular process outcome happening. And again, depending on whether these are categorical or continuous kind of outcomes, then we can use these different distributions to be able to describe the likelihood of these events occurring. Okay, so talked about creating distributions thus far, but we need to be able to sample from those distributions as well, to be able to extract values from them. So when we have a known distribution that we've fitted to our data, we want to be able to get some values out. And this can be done using sampling functions for particular named distributions. So for sampling, different sampling approaches that you get are for for name distributions in R is that they generate random numbers, a set of random numbers based on a defined distribution. So what we can do is directly sample one or more values from a distribution, or we can generate a set of two or more values from a distribution and then sample from those. So it's two slightly subtly different sampling techniques there. We either simply sample a set of however many numbers that we want directly from the distribution, or we generate values from that distribution and then sample from those. So it's the two-stage sampling in this second version here. And so this first approach is used when you want to be able to sample from the entire distribution with replacement. And this concept of replacement is that when we take a value out, we put it back in and it can be used again. With the second approach here is that we want to be able to predetermine the number or range of values that are sampled from the distribution. So we want 100 distributions, 100 values, and then we are going to sample these, and we can do it with or without replacement. So we can choose to put them back in, and then they could be picked again, or we can do it without replacement, where once a value is used, it can't be used again. So this becomes useful when you're trying to allocate more unique values to individuals, or just have a certain number of people with a particular value within your sample. And so when we're using without replacement, we might say, for example, generate 100 values, and then we want to sample 50 values from there, and we don't want to replace, so all of those 50 will be 50 values will be different from each other, and it's just being able to control that. So when we do sampling, there are built-in functions in R to enable us to do this. So they have the general form of that you get the function name, the number of values that are to be sampled out of that distribution, and then the keyword arguments for the distribution parameters. So the simplest one of the simplest distributions is the uniform distribution, and the name function name for this is when sampling from it is called run if. Not quite sure on the history there. They could have called it uniform, but maybe that name was already taken. But it's called run if, and we define the number of values to be sampled out of the uniform distribution. And then we give the minimum value that can be sampled and the maximum value that can be sampled. So here, what we're saying essentially is I want a uniform distribution where the probability of selecting a value between 0 and 90 is equal, and I would like to sample 100 values from that distribution, and this is with replacement. So while the probability of every value being selected is the same on each turn, so you can get duplicate values within your sample. here. Other distribution sampling functions that we get are, for example, for the normal distribution, we use the R norm, so random normal sampling. And again, we say how many values we'd like to sample. And the normal distribution is described by two parameters. Its mean and its standard deviation, which is the spread. The exponential distribution uses random R EXP, random exponential sampling, and we're selecting 100 values, and exponential distributions are described by the rate parameter, which is the rate of either decline or incline on the slope of the curve. For the Poisson distribution, we use R-Pois, random Poisson, and that is described using the lambda attribute. For the log normal, we use RL norm, random log normal, and this is because similar to the normal distribution, it has two parameters, and these are mean log and standard deviation log parameters. And again, these give where the log mean sits, the mean, and what the log standard deviation is around that mean. If we want to sample from distribution values that we've already sampled from, a known distribution, the arguments here are the vector of values from which the sample is to be drawn. So, for example, we have gone and we've sampled 100 values, for example, from the this normal distribution, and then we're passing in that vector our normal variable here, which is a vector of values, 100 values drawn from the normal distribution that we've defined. And then we say how many we want to extract from this subset of the normal distribution. And then we can choose whether we want replacement or not. So this is where we put the values back in so that they have the same probability of being sampled again. And this is done using the sample function. And this, like the it is using a uniform distribution. So each value has the same probability of being selected. Okay. Little task here. We'll just have, sorry, I'm just trying to see what the time is. We will have 15 minutes, no, 20 minutes. We'll do 20 minutes. We'll go to 15:15 on this. Try creating some different distributions using the functions that we've just looked at. Change the input arguments to examine the impact that this is having on the shape of the data, how the different distributions are being squashed and pulled, and how changing the parameter values impacts that with small changes or large changes. and you plot them using the hist function, and try changing the number of bins in your histogram to get different levels of resolution on the sampled data, so that you can see into it a little bit more and try and get the right one, so you can really see the shape of the data that you're sampling. And if you'd like to try and find any more different distributions, do have a look, do a little Google around and try sampling from those. But yeah, have a look at some of those, and I'll pop you in your breakout rooms and we'll come back together at 12:15, just for a little bit before going for lunch. Fitting. We're going to go into the details about distribution fitting after the lunch break. So a basic distribution fitting process it is all about looking at the shape of your data. You need to understand what it looks like and form some expectations about how what type of distribution it should be fitting to. And then you go ahead and you test that. You fit your data to likely distributions. And then it's all about checking how well your guess about what distributions you should be using, how well they do actually fit the data. But as we'll see, this is quite the art form. So a few points of warning about this distribution fitting. Why can't you just use your real data? Why bother using a distribution at all? So your sample of data in most circumstances is only a sample of all of the possible values in your population. And because of this, we need to actually know what the rest of the population might look like and allow for that additional variance that is going to occur within the rest of the population and try and get some estimate on that. The use of real data in a stochastic model causes something called overfitting. And this means that we lose that variation that helps us to generalize our model to other situations. So we actually need it to be a bit different to we need our distribution to be a bit different to what our real world data is, essentially. And that really does help us better approximate the population. What do I do when multiple distributions or no distributions fit my data very well? This is a common issue that crops up. So distribution is as much an art as it is a science. When you're working with messy data as healthcare data is, we're not working with highly controlled data sets here. These are human systems that we're working with. And it really does rely on a process of interpretation, experience, and perseverance. That it's all about, and you get more familiar when you look at a data set. The more that you look at them, the more you can see the different shapes in them. And you gain that experience about choosing which distributions to use, and also just persevering and trying different distributions, going to your model, seeing how they work in the model itself, and then tweaking those distributions afterwards, and perhaps going back and refitting because it's not working in the model. So there's this validation process that has to go on with the distributions that you've fitted. And this is just because real world data is messy. You will have to try multiple distributions, and it does take tweaking them until they work within the model and start producing and do work properly. Another common question that pops up is, I've got 1 million data points. Should I use them all? And the answer to that is definitely not. Again, using too many data points will cause overfitting. Our data just becomes too close to this real world sample that we have, and that it won't give us the variation that we need to generalize outside of our sample of the population. Kind of a general rule of thumb that's commonly used in modeling, and that I've been told over the years, is to use between 2,000 and 10,000 data points when fitting a distribution. There are tips and tricks for using more data points and for using less data points, but just as a general rule of thumb, 2,000 to 10,000 data points tends to work well. And this is actually something that you can tweak when fitting your data, that you might want to start by fitting just as if you've got 30,000 data points, randomly sample 2,000 from it and try fitting them. Then you might want to try a different 2,000 sampled data points and try fitting them. Then you might want to try 10,000 data points and see if you can get a better fit, and just work backwards and forwards in an iterative process like that until you're happy with the fit that you're getting on the data. And a thing to be aware of is that the greater the variation in the data, the more data that will be needed to estimate that variation. So when your standard deviation is very high, you're better off using more data points. So what we're going to do after lunch, and we'll break a little bit early as that didn't take as long as I thought it would, we're going to go through a full distribution fitting process. We're going to talk through it, and then you'll be able to have a go at fitting some data. But we'll talk through the different tips and techniques for actually looking at the data, and different techniques we can use to assess the goodness of fit of our distributions. So we'll get an extra 5–10 minutes for lunch, and we will come back at 1:30 and do some distribution fitting, and then we'll be looking at Shiny after that. So thank you very much. Enjoy your lunch, and I'll see you in a bit. Thank you for hanging on there, everybody, through the little bit of technical sorting out needed. Right, we are going to continue on with looking at distribution fitting, nitty-gritty of how we do distribution fitting with the FitDist R+ package. So what we're going to do, we're going to go through the distribution fitting process kind of step by step, and then you'll be able to have a go at fitting a couple of additions yourselves. All of this code that's on the slide is compiled in the fitting task code. Just going to turn my camera off. My internet seems slightly slow. All of the task code is in the fitting task code R file, although so you don't have to be, you can just sit back and relax, and I'll talk through this, but you might want to make notes in the task file itself, or elsewhere, however you're doing that. So the distribution fitting process, what we need to do first of all is load up our packages. So the main one that we need here is the dist r plus package, and I've imported here ggplot2 just so for a little bit of practice around using ggplot. So what we're going to do here is, in this example, I've used the set seed function, and like you might have seen in Python, you can control the random seed that is used, always get the same pseudo-random numbers being produced. So the function for that is set.seed in R, and here we're just setting that to 12. And it's just if you do that, if you go through this, then you can do the same to bit of data that we're going to use for plotting. And kind of for this kind of example usage, this is helpful because it enables us to just work with a known distribution and random log normal function to select 1,000 data points using the parameters a mean log of 2.7 and a standard deviation log of 0.6, and assigning that to my data. And then we can produce a scatter plot of that data. And this is what that scatter plot looks like. And as we discussed earlier, we can start to see a bit of the shape here of the data. More values down the bottom, as if you're remembering now, different shapes of different distributions, we'd expect to see more lower values, but given that the log normal distribution is negatively skewed, and then there being, and as it tapers off, that there's less values at a higher level, higher range, at the higher end of the range even. That's the words. The next thing that we want to do is use a histogram as a more useful way to plot this data. So creating a histogram using ggplot2. Here we turn our vector of data into a data frame and giving it the column header data. And that's indicated by these quotation marks, so saying I want to assign my data not just as a data frame, but giving it this column header here. And then we can plot that. So assign into the gg2 plot object data as the data frame df, and then using the plus operator, adding a histogram geometry layer, and in the mapping in the aesthetics to X the column data in our data frame df, and then deciding here I've used 10 bins in the histogram and just given a bit of a black outline and grey fill to the bars on the histogram. So this is the histogram that is returned showing the data. And when we look at this, it starts to show the classic signs of being a log normal distribution. Here we see a heavy negative skew to the data and a fairly long tail, a sharpish decline and a long tail. So these are the little features that you start to see in different distributions, and that you can visually start working out what distribution your data might be. Here we know that, but it's useful to work with known distributions and understand their characteristics as well. What the data looks like and trying to think about questions you might ask yourself. So if you have symmetry in your data, in your histogram plot, then there's a possibility that it's going to be a normal or Gaussian distribution, as that is symmetrical about the mean. Another one is to ask, is it positively or negatively skewed? And again, this will tell you if it's perhaps a beta distribution, which is positively skewed, versus a gamma distribution being negatively skewed, or whether it might be a positive or negative exponential distribution, those being positively and negatively skewed. And seeing if just which way data is leaning, whether there's more higher values or more lower values. If there's one or more modal values, mode being the most common value. And for example, sometimes in some data you get bimodal or multimodal distribution, multiple common values. And those require special techniques to fit distributions to them, sometimes splitting the data distribution up into multiple distributions, or there are some more complex techniques for looking at particularly bimodal and fit into bimodal distributions. Is the mode the lowest or the highest value? And that will indicate whether it's likely an exponential distribution. So there's a few little points just to see, testing this particular distribution or this, you should be which distributions you should be testing. As already mentioned, there's no symmetry in this. It is positively skewed, it's not indicating that it's not an exponential distribution. So the mode is, and there's only one modal value here as well. I apologize if my internet is cutting out. I'm going to carry on talking so that the recording's made. If it does become annoying, then you either wait for the video to come out and go back over it, or perhaps just try and follow through on the slides, and I guess kind of do your best with it. I apologize for the connection issues. At our plots here. we can go and look at, we can start drilling down into it and using some of the functionality in our for distribution fitting. So coming from the distfit R+ package, we are able to use a function called plot dist to plot the PDF, the probability density function, and the cumulative density function, the CDF, of the data. So if we remember, the PDF, the probability density function, or also what is referred to as the empirical density, the scene density of the data. This is equivalent to a histogram, giving the probability density of the observations, probability of a value falling within the range, within a given range on the histogram. Then we also see the CDF, which adds up the probability density of the observations. It's two different ways of viewing the same thing. And so into the plot dist function, we put in the data that we're going to use. So this is our vector of data, my data created at the beginning. And we're going to ask it to give the histogram so that we can see the histogram on the probability density function. And we'd also like the empirical density given as well. So we put both of these to true. So what do we get when we use this function? So these are the probability density function, the dashed line here on top of the histogram, for the empirical density or probability density function, and the cumulative density function, this cumulative distribution here. And these, again, they start describing the shape of the data, but in a very literal way. This is what would be considered an overfitted distribution of the data. So we would not use the PDF, the probability density function, directly to parameterize a model. It is too heavily fitted. So now that we've got our PDF and our CDF of our data, we can move on to assess something else about the data, which is its fit in terms of its skew, which is why this is so important, this positive and negative skew of the data, and the kurtosis. And this is all to do with the sharpness of the peak of the curve. And this value says how gradual that hill is, that peak. Is it a sharp peak, like we see in more the log normal distribution, or something more gradual that we see in something like gamma distribution? And so the process that is used in R is something called a Cullinan-Frey graph. And there's different arguments around what it should be called online. Statisticians will argue to the ends of the earth about this, but in the documentation for the FitDist R package, you'll find it's referred to as Cullinan-Frey graph. And we use the function DESC, so desk dist, standing for describe distribution. And again, we pass in our data as the first argument here. And if it depends whether we are using a discrete distribution, as we were talking earlier, whether we see this as a discrete distribution of solely integer values or a continuous distribution. And we set that to either true if it is a discrete distribution, such as a categorical, a distribution of categorical variables, or of limited integer values. And then this process that the Cullen and Frey graph uses is a simulation approach that uses bootstrapping. And this just means that it looks at it multiple times and tries multiple different fits multiple times with the data. And so we can set the number of bootstrapping iterations that it will run through. And kind of, again, rule of thumb, 500 is often more than sufficient in this, but you can play about with that for greater or lesser accuracy, and it depends on the variability in your data. Yeah, so just a note here that, yeah, making sure that if a discrete, if you are using a discrete distribution, do remember to change this to true. So what's the Cullen and Frey graph look like for this data? So in the this is a Cullen and Frey graph. And we've got here on our x-axis the square of the skewness, and on the y-axis the kurtosis. And they're using a mathematical process here to compare the data, so our observed values and the bootstrapped values produced through simulation, against different the expected values from different distributions. So up here we have legends that give different theoretical distribution outcomes from common named distributions. So we've got the normal distribution, uniform, exponential, logistic, beta, log normal, and gamma. And just a note that Weibull is close to gamma and log normal. So what we're looking for with our data here is whether it fits around one of these, either the shaded area, these lines here, or on one of these points. And so if we note here, the uniform distribution is right up here in this top left corner. And you can see that the skewness up there is 0, the square of the skew, and the kurtosis is close to 1. And that's because the uniform distribution, all values in that distribution are even. They have an equal probability of occurring. So it's just flat. So there is no skew to the distribution, and there is no peak. The normal distribution, however, that also has no skew. So, which is why it's over here on the left-hand side of the graph. But it does have a peak. And that is why it has a higher kurtosis value. The logistic regression, the logistic uh, sorry, losing my words, the logistic distribution, again, it has no skew, but it has a sharper peak to it. Interestingly, if you look here, because the relationship of the normal distribution and the log normal, gamma and beta distributions is that they are skewed versions of the normal distribution with sharper or less sharp peaks. The exponential distribution, and that's why they originate from the normal distribution here to this point here on the graph on the top left corner. So as these distributions become more skewed and with sharper peaks, we expect our observed values to come further down towards the bottom right corner of the graph. So these are just an interesting visualization of the relationships between different probability distributions of data. The exponential distribution sits here in the middle, as it doesn't really have a peak per se. It is just a slope itself. So it is skewed all the way either to the left or to the right, so positive or negative skew, and which is why the square of the skewness is in the middle of this range between 0 and 8, so at 4. And the kurtosis, the sharpness of the peak, is again around the middle value because it's on there's no peak per se. So when we actually look at our data in relation to this graph, we see that the observed values, the observation sits here in to a kind of just it's not on the exponential, so it's probably, you know, we know it's not an exponential distribution, so it's good to see it slightly away from that. But it is close to that because it has quite a sharp peak, which is why it's around the middle values. And then in terms of the skew, it's heavily skewed over to negatively skewed, so skewed to the left-hand side of the graph. And if we look at the bootstrap values, they are falling actually more around the gamma distribution, but towards the log normal as well, and straying towards beta. So if we weren't sure what distribution this was, we would probably look at this graph and go, okay, we should probably be testing the log normal distribution, the gamma distribution, the beta distribution, and perhaps the exponential distribution, and to just have a look across these. And because Weibull or Weibull distribution is close to gamma and log normal distributions, we should probably test that as well. So there's a note in here just saying so the gamma, the observed values are actually, they seem closer in this graph to the gamma distribution line, and this is a little bit misleading, and we will see why. This is one of those things, which is why we go through these multiple different processes of assessing distribution fit. So now we've got this idea of which distributions might be fitting our data best. We now go through the following process. And we're going to visually assess this fit using the theoretical probability density function of those named distributions, the theoretical cumulative density function of the named distributions that we're testing. We're then going to use a QQ plot, which is the comparison of the quantiles, and is quite a sensitive way to test the deviation of the quantiles from the empirical probability density function and the quantiles of theoretical empirical density function. Then we're also going to look at a PP plot, which is a comparison of the cumulative density functions of our observed data, our real world data, and the theoretical ones that we've fitted when we fitted our data to these distributions that we're testing. And what we're looking for is deviation of the theoretical from the empirical data. And we'll see how that works in a moment. And then we're going to go on to calculate some statistics around the fit of our data. And that's going to be looking at goodness of fit and some uncertainty estimates around the fit. Then we're going to go on, and then you go on to select the best fitting distribution and extract the distribution parameters from the R output. And then you can go on to use those parameters in your model, or go on to retest using different distributions if the fit isn't good enough or not as good as you would like. So, first stage in this, it seems like a lot. It's not as bad as it sounds, I promise. And it's actually very little code when it comes down to it. So we use the fit_dist function to fit a particular distribution to the data and obtain the parameters for a theoretical fitted curve. So we use the fit_dist function, pass in our vector of data, and we give the name of the distribution as a string here as the next argument. So I want to fit the data to the Weibull distribution, and then I can get a summary of the fit_dist output by calling the object to which it's been assigned in summary function. Within this, by default, the maximum likelihood estimate method is the one that's used to estimate the fit and the parameters. There are other methods. However, I've got to say, maximum likelihood estimates just generically across most common distributions is a good estimation method for distribution fitting. But there's a link here to the FitDist function so that you can have a look at different options should you wish to try them out. So when we call the summary output from the FitDist function, what we get is this output. So it tells us which distribution we're fitting to, and that the method that it's being used to estimate the parameters. So this is using maximum likelihood. And for the Weibull function, there are two parameters that it requires, and that is shape and scale. And these are the estimated parameters here. So these are actually the parameters that if we were to produce a random Weibull distribution to produce some values, these are the two values that we would input. And so for the time being, just knowing that these are the parameters that are then going to be used to produce the theoretical PDF and CDF. So to expedite things, we can fit more than one distribution at a time, and we can do this using lists and loops. So a quick way to do this is to produce essentially a list of names of distributions that we want to fit, create a blank list, and then we iterate over the dists object, pulling out and fitting each name in turn. And then we can also print them again in turn. And so by fitting these multiple distributions, and then you can just print them one after the other. So you can compare multiple distributions at a time. And here we can see that, so for example, for the gamma distribution, this might be a little bit small, I apologize, but we can start to see that the for the gamma distribution, the parameters that are required are shape and rate. For the log normal distribution, it is mean log and standard deviation log. And for the Weibull, as we saw, it was shape and scale. So it's always outputting the right parameters that are then needed to create the theoretical distribution in other R functions. So now we've got our fitted distributions, and these fitted distribution objects that we've created here, these summaries, we use as the input for our other for our further analysis. So what we now want to produce is our comparison of the empirical and the theoretical PDFs, empirical and theoretical CDFs, and then QQ comparison plots and PP comparison plots. And so this little bit of code here, don't have to do this way. This is just a way to condense the output. I'll go through this line by line, as that's the easiest way to do it. So what we have here, this par function is setting the parameters, the print parameters for the output. And here we're saying that we want the plots output as a 2x2 in a 2x2 grid, 2 rows and 2 columns. Then our plot legend is going to be from lists, which is, go back, I think the internet is cutting out again. Our lists here are the names of our distributions. So we're just passing in those names to the legend so it knows what to call each distribution in the legend. And then we've got 4 functions that we're calling. We're calling the density comparison function, the CDF comparison function, QQ comparison function, and the PP comparison function. And to each of these, we're passing the list of fitted distributions. So this is it can be one individual distribution if you just fitted one, but it can be more than one. And that's why we're passing into the legend text argument here our plot.legend, passing in the distribution names. So what do we get as our output here? So I've got these coming out individually, so they're nice and big. And this is what happens if you omit the first line here, the parameter setting function, to output it as a 2x2 grid. So our PDF comparison. We can see here that we have the legend saying our what the names of our distributions are, and the histogram describing our real data. And each of these curves shows the theoretical probability density function for the named distributions. And here we start to see that we can look at the shape of our curves and see which are fitting best. Now, if we look at Weibull distribution here, we can see that the peak is actually quite a bit lower than our modal value. So that's not a great thing. You know, we want to be estimating our most common value much better than that. It also starts, it overestimates the probability of our lower values. So it's estimating these just much more highly than we might otherwise like, because there's not that many of these lower values. The gamma distribution appears to actually estimate our modal value really quite well. You know, it's right, the peak's right on the top of the modal bar there. But there's also a slight overestimation here of these values following on from the modal value, and it also overestimates our early values as well. The log normal distribution here estimates very well our early values, slightly overestimates the modal value, but it also much more, it has a better of the values following how the different distributions are estimating the empirical values. And it's just learning to start interpreting these different aspects of the PDF. If we go on to look at the zoom in on this a bit more, comparison of the CDFs. It's a little bit harder to see here, but you have an opportunity to play with this and have a look at the visual fits yourself. We are looking at the deviation of the lines from the black dots. And again, what we see here is that we have this is what we're getting. We're getting underestimation, overestimation of the these low values here, first of all, and then underestimation of these values here. We've got much greater deviation for the gamma and the Weibull distributions, whereas the log normal actually fits fairly well within the area of the black dots. So we're getting slightly different stories from each of these graphs here as we go through, which is where this becomes a job of interpretation. Oh, I've got a question from Andrew.
Yeah, hi, Sean.
Hi there.
Wondering on the previous one where you had the histogram and the theoretical density.
Yeah.
So exactly which bits are we comparing? I'm just wondering, given that we know it is actually a log normal, is it in fact that if we look at where our dotted green lines in the center of the bars, that is pretty much exactly where we expect? I'm wondering if we redrew that with thinner bars, would it look closer? So when you've got fat bars, is it actually the center you're looking at rather than the height of the bar compared with the height of the green line?
Yeah, it's difficult because it's the theoretical density is calculated on a much finer degree than the histogram bars. So they're actually doing it for much smaller ranges of values, whereas here we've the histogram showing between 0 to 10, 10 to 20, 20 to 30. And so yeah, you're looking at across the bar really, to be honest, because that's what the theoretical distribution itself is doing. So it's kind of, it's more that you're looking, it's trying to fit one shape into another, which is difficult to explain actually, that because you've got something represented, something continuously and something is in a discrete way. But it's across the range of the bar is actually what you want to be looking at, rather than seeing where it's hitting on specific points on the bars themselves, if that makes sense.
Yeah, I guess so. So I guess that 10 to 20 bar, because the green line's above it at the beginning, but below it at the end, probably does average out to around the height of the bar. Yeah.
Yeah, it's this. So as we go across the range of the bar, that we're seeing what values it's estimating. So here we're perhaps estimating the value of 2 at 0.008, probably something like that. And so it's across the whole range, but you don't see that level of detail with the histograms that are produced out of this function, unfortunately, which is where you need to use all of this information together, and it's an interpretive exercise that it's not hard and fast. It's taking lots of different information together. But yeah, you want to be looking across the ranges of the bars.
Okay, thanks.
Okay. No, good question, and it's a difficult thing to get used to. I mean, it's taken me years to learn how to do this to my middling degree of being able to do it. It is a difficult technique, especially with small samples and with messy data. So just one that takes a little bit of practice. But yeah, the CDF is much easier to look at, and the deviation is much easier to see here on the CDF itself. So once we've had a look at both the PDF and the CDF comparisons, we can go on and look at the QQ plots, which is where we are comparing theoretical quantiles. So here, what we're looking for is it's not about understanding too much about what the quantiles are meaning. What you're looking for is the lining up of the points, of the quantile points, along this linear line here. The linear line is representing the empirical quantiles, and then the theoretical are given by the colored points. And we can see that we're getting much greater deviation on the gamma and the Weibull distributions. And this is, again, all pointing towards this being a log normal distribution. Even though in our Cullen and Frey graph, if you took just that, you would probably be hedging your bets towards it being a gamma distribution. So all about looking at multiple sources of information together. When we look at, sorry, I should probably just give you a read on this text. So, so yeah, again, this kind of process is similar to the least squares methods, where you're seeking to minimize the residuals, so the deviation between theoretical, between empirical and theoretical. And again, we look at this for the theoretical and empirical probabilities. And here we see that the deviation, there's very little deviation, in fact, only at certain points where we get a small amount of deviation in the log normal distribution here. So we're looking that for them, the one that best lines up along the black line, the linear black line here. So this is all indicating to me that this should, the log normal distribution is going to be the best fit for us from a visual appraisal point of view. So that's looking at visual parameters. Now we can go in and use some more mathematical techniques. So using particularly goodness of fit statistics to assess the fit of the empirical and the theoretical distributions. In R, this is done using the GOF stat function. So goodness of fit statistics. And here we pass in our fitted distribution data, and we pass in the names of the distributions as well. And so when we output the goodness of fit statistics, this is the output that we get. And what it's done is it has fitted 3 different goodness of fit statistics here. The Kolmogorov-Smirnov statistic, Kramer von Mises, and Alice Anderson-Darling statistic. They're all just slightly different ways of calculating goodness of fit. You have to ask a statistician for the real detail of the differences between them. And there's also this goodness of fit criteria here as well. Akai's information criterion and Bayesian information criterion. And these are actually given in the distribution fitting parameters. So I'll just scoot back up here so we can see the example. These are the AIC and the BIC given here in the fitting using maximum likelihood. Oh, sorry. And these are basically prerequisites or assumptions for a goodness of fit test to see whether they are close enough to, or the distribution is of sufficient size and detail and of type to be able to fit to use goodness of fit statistics. And when it comes to actually interpreting these statistics, we are seeking to minimize these values in the goodness of fit statistics. And we can see here that if we look across on each of these statistics, the lowest one in comparing all of them across all 3 statistics is the log normal distribution. So even though the Cullen and Frey was misleading to start off with, our visual inspection of the empirical and theoretical density functions and the statistical assessment of these distributions, we can see that both of those are pointing to it being the log normal distribution that fits this data the best. In the goodness of fit data, there is a whole raft of information in the background there. And you can go in and we can see in particular that it actually gives rejected or not rejected decisions in there. So these are for the Anderson-Darling, the Komologov-Smirnov, and the Kramer-von Mises tests. And so for each test, it goes across and gives a rejected, not rejected, or not computed outcome. And the here we can see with the Komologov-Smirnov test, which is the main, more generic type of test that doesn't require too many different assumptions with it, but also is kind of tends to be the overriding goodness of fit statistic. This rejects both the gamma and the Weibull distributions, but does not reject the Komologov-Smirnov, the log normal distribution. And there's also a whole lot of different information that is also included in the goodness of fit outputs that you can go in and you can, if you're of a statistical bent and would like to interrogate that, that is very much, you know, you can get into that. We also tend to see that things like not computed or rejected is not uncommon for all of the distributions that you're testing, even though visually they look like a good fit, to be rejected using goodness of fit statistics. It really is not so common. And this is why we use both visual inspection and statistical inspection of distribution fitting, because they can be very finicky, the statistics, and you cannot rely on a kind of black and white output of rejected or not rejected. That will just lead you to madness, because you will end up never fitting a distribution to real world healthcare data. I can tell you that now. But rather, it's a case of finding the balance between the number of observations that you're using, the type of distribution that you're fitting, and then the tests that you're using to fit those distributions. And it has to be a bit of a fluid kind of process, an iterative process. Yeah, but it is one not to drive yourself insane, and I have seen this in other people that we've worked with, driving themselves crazy trying to get perfectly fitted distributions that are both visually and statistically compatible, and it is, you could spend months doing that. We have other things to do, I believe. Get a good fit on your distribution and validate it in your model, is my advice. So looks like we've got a pretty good good fit on our data here, though, as we should have done. You know, I'd expect that with that we've used a known distribution to extract this data, so it's no surprise that it fits the log normal distribution. We can do some, so the fitted distribution parameters are only estimates of the true distribution. And the boot dist function here is a way to estimate the uncertainty around and the confidence intervals around the parameters. And this is really good for when you want to tweak the distribution in a model when you're implementing it. So you will not, when you actually implement it in your model, it might start producing some spurious values that you're not quite happy with, or it's estimating things a little bit low or a little bit high, and you just want to tweak the distribution a little bit. So what you can do is use the boot dist function. Sorry, it's hidden in this loop here because it doesn't take a list of inputs, so we have to do it in a loop. But it's this line here where we're passing in the individual distribution fitting, the theoretical distribution parameters to the boot dist functions. And then because it's a bootstrapping, it's a simulation approach that's being used for the parameter uncertainty. It's running a series of iterations. So here we're running 3,000 iterations on to estimate the uncertainty around the parameters. No, it's 1 times 10 to the 3. So 30. So and here, this is the output that we get around parameter uncertainty. So this provides us with the median values of our parameters. So here we see shape, rate, mean log, standard deviation log, shape and scale for each of the different distributions, their median values, and then their upper and lower confidence intervals as well. And so what you can do is to be able to tweak your parameters when implementing them in your model between these values, these upper and lower confidence intervals, just to give you that little bit of flexibility to be able to tweak it. And these are useful when reporting your parameters in a model. So the fitted distribution parameters, what are we taking away from this? So we've gone through this whole process of visually, we're looking at our data, we're fitting distributions to it, we're visually assessing the fit, we're statistically assessing the fit, and looking at the uncertainty. Now we've picked which distribution we want to use, and we want to use it in our model. So let's get that data, let's get that information and what you can use in your model. So this is going to be the log normal distribution. From our distribution fitting data, we're getting our mean log and standard deviation log estimates. So we take these estimates, and then we take our, if we want to, might want to tweak our parameters as well, we can take our upper and lower confidence intervals and use them as bounding for tweaking our parameters in our model. So it is these estimate values and these confidence interval values that we want to extract. And given that our original distribution parameters, if you remember back to that, were mean log equals 2.7 and standard deviation log equals 0.6. And here we see that we have an estimate of 2.68 and 0.57. Whereas when we look at the lower and upper confidence bounds, they nearly encapsulate that So we get 2.71 as the upper confidence bound, as our estimates are slightly low. The upper gives 2.71 or 72 even as our upper confidence interval for the mean log, and 0.598, which is essentially 0.6. So here we're seeing that our estimated parameters are a little bit lower than our known parameters here for the fit. But this bit of difference as well is what gives us this flexibility and the variability and stops and prevents us from overfitting in our model. So it's not a bad thing, that, because this is an estimation process. It's estimating from a sample and trying to estimate to more of a population level. So I think it's about time that you had a go at doing some distribution fitting yourselves. Let's just see, what time is it? We are... Okay, so the fit it exercise. In the so in the GitHub repository, you will find the dist fit folder, and in here you'll have the fitting task code and fitting task CSV 1 and fitting task 2 CSV. It's so your task is to use the fitting process that we've just discussed to fit a distribution to each of these data sets and estimate the parameters. There is the script fitting task code that contains the basic code needed for this task, or you can choose to use that code, or you can write your own script. What I'd like to do is have a go at fitting to these fitting distributions and finding out what distribution best fits this data. You actually, you might want to produce some of your own data or try fitting your own data even. But the key one here is to have a go at fitting some distributions to some data. So I am going to put you in your breakout rooms in a moment. Going to have, we'll run till 3:20 on this exercise. And then we'll come back together and we'll have a little look at Shiny apps at that point. We'll come back at, so 3:20, we'll come back, have a go, help each other out, use the reference material here, and also make sure to have a look at the distribution fitting resources if needed, the documentation for the package if you want to drill down a little bit deeper, and yeah, have fun with it. Welcome back, everybody. I hope that that went okay and that you managed to get a little bit of practice in with fitting data to different distributions. It's something that is best just to practice and that you'll get used to over time, but hopefully this gives you a template really for being able to do distribution fitting in a kind of systematic way that gives you enough of the kind of idea of how it's working and how things are functioning. So just share my screen quickly. So there is a package called Actua, which works with the FitDist-R+ package to extend the number of named distributions that you can use. I'm not going to go through it now, but there are a number of distributions in there, and it's one that if you do get into distribution fitting is worth having a little look at. There's links here as well in the slides for distribution fitting resources around both of these packages, which are just great references as they go into the nitty-gritty detail of the distributions, how the different functions are working, and you can delve into as much of the stats and the maths as you would like to. So we've got about an hour left, and I'm going to give a brave attempt at teaching you at least the basics about web app development using Shiny in an hour. And so we're going to go through looking at the kind of the structure of an app, the layout, the how to build in functionality, and I'll discuss a little bit about app deployment. I don't think we'll get onto the exercise here, but I'm going to show you first of all, just before introducing Shiny. Well, before introducing Shiny, I'm going to show you an example app. So the app that I'm going to show you is available in the rShiny folder from the GitHub repo, and it is under dist fit tool. And in there, not all of these files will be in there, but you're looking, it will be simpler than this. Sorry, these are my local files. But what you'll find in there is the app.r file. And if you go into that, this is the template for the start of a distribution fitting app. So with Shiny, when you import the Shiny app, the first thing you'll notice is that the run button changes to run app. So I'm just going to run this. And this gives us a basic distribution fitting tool. It includes a data upload bit where we can go in and upload some data. So when I upload the data, it produces the empirical density function and cumulative distribution function for me. It's actually populated that. Shouldn't have populated Cullen and Frey graph, but it has. So we can pick some distributions here to look at as well. So I can put in the log normal, and let's go with gamma in there as well. And I can do goodness of fit and select uncertainty as well here to look at. And then we can scroll down and we can see these outputs, the comparison of the PDF and the empirical and theoretical PDFs, and the comparison of the CDFs as well for this data. Then we also get the QQ plots and the PP plots as well. Then we can go over to the tables tab here and just give it a moment to populate. Here we get statistics from the Cullen and Frey graph around our data, so estimating skew and kurtosis, mean and standard deviation. Then we get the fitting summary for the distributions that we've selected, the goodness of fit summary as well, and the uncertainty estimates as well there. So this kind of just gives you a tidy little app to be able to drop some data in and flip around and compare multiple distributions. It shows us the raw data here. The one caveat that I have to say with this particular app is that I have not built in the functionality to test discrete distributions yet. So if anybody would like to extend and use this app, a good place to start would be by building in the functionality, a little option to select whether it is a continuous or a discrete distribution that you are using. So just highlighting that caveat there with this. But yeah, you can use it as the base, perhaps use it as the basis for your own distribution fitting tool if you find that's something that would be handy. So how was that app built? Let's have a look. Just going to clear my histories here as we're going to start looking at some code shortly. So RShiny, it was developed by the RStudio group as a way to develop interactive web apps within R. And this isn't something you can normally do because R isn't developed for object-oriented programming, which is generally required for web applications or something. It needs to be able to run that in the background. It is done as or it's shown as a way of developing web apps with no web development skills being required. I put the caveat in there, kind of. You do need some web development skills, particularly when you get onto deploying the app itself. And they are deployable and scalable apps. The NHS, I mean, you might use examples of Shiny apps yourselves that have been developed by NHS England and NHS Improvement. I know that they're doing a fair bit of work around that. In fact, one of the MSc students at Exeter last year for their MSc project developed a Shiny app, and another actually developed an app in Python for demand and capacity planning. So you might see them coming online soon. And RShiny can be extended with additional HTML, CSS, and JavaScript to bring in different formatting and functionality. So what are these apps comprised of? Well, there's three main components. This is the app layout, so the user interface, app functionality, which is the server, and the app run command, which runs the layout and the functionality together. So the app layout. this is where you define the input and output components in the app and their position on the page. And so kind of a generic template for this is that you define the type of page that you're going to be using, and within that, so it's kind of this overall overarching page type that you define. Then you add in navigation components first of all, then individual input components, followed by individual output components. And these are all assigned to a object which you tend to call UI. So that's your user interface. So let's have a look at a layout example. And in here, we're going to be using a few different types of block. So we're going to have a title panel. We're going to have give it a sidebar layout, saying that we want to have it with a sidebar and a main panel. And then we're going to be able to add in our side panel component. We're going to put in a header. And if anybody remembers from Dash, we get these HTML conventions, which use for header components, we use different sizes. And here we're going to use H3. We're going to use a paragraph component, P. And we're going to give have a main panel component as well. So the one, if you're looking at the code live yourself, you'll need to go into the layout example folder and open the app.r file in there. And so let's talk through this. Obviously at the top of our code, we're bringing in the Shiny library. And so we can see that it's recognized that Shiny is installed, and it recognizes the library because we've got run app button instead of just the normal run button. And so we start by defining the page layout type. And there are a few different layout types. It's very limited because Shiny is limited for web development to make it easy to use. But you get either basically a static page where the layout doesn't change depending on the page size or the page size or the screen size. Or we get things like a fluid page, which is entirely that it's what's called reactive CSS, and it will change the layout given the size of the window that it is in. So here we're going to use a fluid page, which is a good standard starter one. And we're just going to add in our components. So we're going to put a title panel into it. And this takes a string of text to say what you would like to include in the title panel. And here I've just put my first web app. Then comma separating these components, added in, we said that we want a sidebar layout now below our title panel. And so open brackets, and then within the sidebar layout, we are then including a sidebar panel. And within the sidebar panel, adding a header, which takes a string of text, and a paragraph, which takes, again, a string of text. And that's all that's going to be contained in our sidebar panel. So within the sidebar layout still, we're then going to define the main panel as well. And so the main panel is, again, going to just contain header text and paragraph component. And that is just this block here. So both, we've said that we're going to use a sidebar layout, and within the sidebar layout, we are defining both the sidebar panel and the main panel. And then further down here, we have here the server part, which is where we're defining functionality. And at the moment, our app doesn't have any functionality in it. So it only has this call to function, input, output, and curly brackets go into server, because it's just nothing's happening. And that means that we can pass, we have a UI object and a server object that we can pass to our Shiny app run command. So let's, if we now run the app, so you can see it's opened in this smaller window. And if I open the window out, the sidebar panel moves over to the side and the main panel moves over to the other side. If we make it small again, they go underneath each other so that you can see them. This is the fluid layout that you can see here. This is reactive CSS, and it's changing. It's all built into Shiny, which makes it a very easy development environment. It means that using this kind of fluid layout, things will move around and make it, try and organize things in a way that works best for the screen size that you have, because you could open these on a phone, for example, in which case a sidebar layout might not be the best thing to use. So that's just getting basic layout with no functionality, but we can start adding in components and just bringing in our different components and laying them out. Right. So another useful thing, if you noticed on on the previous on the distribution fitting app that I demonstrated first of all, it was using tabs, and they're really useful for organizing presentation of components, and means that you can contain more components than you might have space for on just a single page. So for this, we use a tab set panel, which is initiated in the layout, and we can initiate it either in a sidebar panel or in the main panel as the main tab component contain. And then tab panel components are then added to within the tab set panel, and these are the individual tab containers. Your individual tab panels sit within the tab set panel, and then within each tab panel you can add components that you want displayed within a given tab. So just quickly show you an example of that. So here we have, again, the same start to our code, that we have our UI object, and we're going to use fluid page. Going to add a title panel to it, and then again use a sidebar layout. Our side panel will remain exactly the same as previously, and then when we declare our main panel, within that we're going to declare a tab set panel. And there are a couple of different types of kind of styles of tab that you can use, which are either more look like buttons, or that look like tabs. But here we're defining tabs, and then we define tab panels, which are our individual tabs and what is going on within them. And the rest of the app remains the same. So if I run this, we can see that here we get, again, very similar to the layout example. Got our title panel, our sidebar panel, but then within our main panel here, we have our tab panel, and we have our 3 tab panels. So we got one here, plots, place some plots. Can have some summary statistics. We might put a raw data table in here. And it is only that very small amount of code that is required to build up this kind of functionality in Shiny, which makes it really user-friendly. So just a few lines of code give us tabs. And then any components that we want to add on top of that can be built up within. There is also an advanced tabs example, which contains what have we got in? I can't remember what was in this one actually, sorry. Yeah, okay. Yes, I remember now. So what we have here is, this is kind of a distribution sampling example. So here we're using tabs, and again, we can have different pieces of information within our different tabs. And this one, we can select the number of observations being drawn from a different random distributions, just for a bit of fun. But that gives you an idea of how to embed functionality within tabs themselves. But we'll come to that. We won't actually cover all of that, but I just wanted to point out that it's there if you're wondering how that all works. So, okay, yeah, let's look at getting some functionality into our apps. And because it's great, okay, we can put all the components that we want in, but how are we going to make them do anything? So previously, we had our server object, which we weren't actually passing anything to. There was no functionality in it. So generically, the functionality for a Shiny app takes the form of you call function, so the function, and that it is taking the 2 inputs, input and output. It requires both of these arguments, input and output, because these are what we're going to define. We're going to define our inputs and outputs within our app, and they need to be passed into this function. So we then use curly braces, and this is then going to, and those curly braces contain the name of an output component, what we're going to render, a render type. This is a bit of a weird concept in Shiny, but it's basically saying, is this plots? Is it a graph? Is it text? What type of what am I rendering as the output? And then we get an R expression for the which uses an input and takes that input and does something with it to produce the output to the output component. Then we get a function name and a reactive function type. And we'll look at these more in a moment. And then we pass into that an R expression using the component input component value again of something that is being changed within the function itself. So it's easier. This is just a little generic reference for how this layout works, but it's easier to look at it in practicality. So we have to define the use of the input components to produce outputs and then pass the outputs to the output components. So in our layout in this app, the app example that we're going to look at, we've got a plot output, and this is a specific output container for displaying plot outputs, rendering them. And they need to have a unique ID. So we must make sure that our output container has a unique ID. When we're defining the functionality, it's a server function. Remembering the server function is bringing in and passing out the input and output objects for the components. When we define an output, we use outputs, the syntax outputs, with a $sign followed by the component ID. And this is in this way we can define what component we're passing the output to within the functionality. We're going to use render plot, and there are different render types for different types of outputs, but all outputs require a render function. It's just a bit of a quirk with Shiny, and something to get used to. Within the render function, any R expressions that are in there need to be wrapped in curly braces. When we define inputs, we use the syntax input, $, and the unique component ID. And this is in this way we can define the object from which to get a particular value. So let's have a look at the functionality example. So, okay, it all looks pretty familiar at the top, hopefully here. So we start our app with importing Shiny. Then we create our UI object. We're going to have a fluid page. We're going to create a title panel first. We're going to use sidebar layout. We then define our side panel. This again is just going to have some text in it. It's going to have a header and a paragraph component. But this time, we're also going to add a slider as the input here. So the slider input object, this is going to be called, the first thing that you define within it is the unique ID. And here the unique ID is just OBS. The second argument here is a string of text that will label the slider, that will sit above it and give it a little tag just to tell you what to do or what it is. We can then set a minimum value, a maximum value for the range of the slider, and then an initial starting value here. So that's making up our sidebar panel. In our main panel, we've then got a bit of text. We've got the header and a paragraph component, and then we're going to add a plot output component as well. And here, the only argument that we're passing to it is the a unique ID for it, and this is just called dist plot. So here we've defined one input object and one output object as well. Now we can extend the server object, and here we're calling function, giving it input and output. And then within curly braces, we're then going to define our function. So we start by defining what we're assigning it to, which is going to be the, it's an output component, output $, and then the name of the unique ID for the output component, which is dist plot here. And to that, we're going to assign, it's going to be render plot. So this is our render type. We want to pass it a plot to render. We then open our brackets on this function. And then in curly braces, because we're going to define an R expression and they have to be contained within curly braces, we're going to create a histogram. We're going to use the hist function to draw from the our input to the histogram is going to be a series of observations drawn from the random normal distribution. And the number of observations is going to be defined by our input object, our slider input. So we tell it it's an input, $ and the unique ID of the component. So we've got an initial value here of 500. So when the app starts up, this value that will be passed to the number of observations is 500. And one thing to note here, so the default values for the mean and standard deviations on the R norm function are 0 and 1. And we're not going to mess about with those because this is just an example. But this is just showing that we can use this input, the input value from the slider, by calling it using the input $ unique ID obs call there. So if I run this app here, we can see we got our sidebar panel here, and in the sidebar I can place all my input selections here, and we've got this number of observations set at 500, and we've got our histogram, our output, being displayed and rendered here. And this is 500 observations drawn randomly from the normal distribution. If I change this up now to 891, go to 1,000, I can go all the way down to just 99 observations. So here, with just a couple of lines, we've managed to get some quite complex functionality into this app. And if you look, interestingly, so the way that the histogram's been labeled, we can see that the number of observations being drawn, R norm is just used, the R, the function, and the input just as because we haven't defined any labels for our histogram or anything like that. It's just use this as the label, and for the title as well. So that's basic functionality, where we're just doing kind of taking simple inputs and we're not doing anything really with them. What we can go on to do is to do more complicated functionality using something called reactive functions. And these work like user-defined functions in a normal R script. So we're going to here create a function called desk, standing for distribution descriptives. And we're going to render some text out of this. So this, what we're wanting to do is output a string object, and so it will be text that's being output, and we need to use the render text render type here. And the reactive function itself, it can be called from within another function. It's going to be our main function here. So if we have a look at this example here. So again, we have just our standard layout start with sidebar panel, and we've still got our slider input here, selecting the number of observations. But this time in our main panel, we've not only got the plot output, we've also got a text output. And this is called dist text. So down here in our function, in our server objects, where we're defining our functionality, we have, first of all, so we can see here that the plot is being rendered exactly the same. So we're passing still to the plot object. We want to render exactly the same plot as we did in the previous example. However, this time we also want to render some text output as well. So we need another output function, another output object here, which is output $distext. So we know we're outputting to this text output object. And to that we're assigning, it's going to be a render text. And within this, we're calling our function, our reactive function, distDesc. And you can see here above these outputs, we have defined desc. This is the name of the function. And so when we start this function, we use the term reactive to say this is a reactive function. This is going to do something. This is going to take a changeable input and then be used for something. And so here the R expression within the curly brackets is that it's basically is concatenating several strings here. So it's pasting into a single string object the text you have selected, followed by the number of observations taken as from the input object slider object, and then followed by the string observations to plot. And the paste 0 function here, this takes text and numbers and concatenates them into a single string of text. And so it is this single string of text which is being created and passed out by the reactive function here. And that's going to then be passed along to the text output. So if we have a little look at the app here, see again, the app looks exactly the same, except now down the bottom here, down the very bottom, we have the text you have selected 500 observations to plot. And if I change that, you have selected 692 observations to plot. You have selected 242 observations to plot. So in this way, we get this function is reacting every time that the input object changes. It fires the function and passes the new value back to our output object. So it's this kind of workflow of input object. When the input object is changed, it will fire anything that uses, takes it as an input, including reactive functions. The functional fire, it'll then pass the value or the object that's created back to the render function, and the render function will pass that information out in the correct format for it to be rendered by the output object. So in this way, we can build up complex functionality within these apps. Now, one important thing is being able to import data within an app. And so the file input component is what we're going to be using here. That's going to be our input into the app. It requires a unique ID and a label. So it describes what it is. And it can be set to accept only certain types of files, but there's actually quite a list of different file types that can be accepted. But input objects in file imports require a reactive function to read in the data. It's got to be able to pass the data when it's read in. And the first line of the function should be require req input $component and the component ID for the file input component. That is just the standard format that needs to be used when using a data import environment, a data import component. And then we need to read in the data using the correct read function, return the data in the required format. And here we're going to use a table output component to display the data. And that needs to be rendered using a render table function in our functionality to produce the table objects that will be passed out. So just have a quick look at the import example. So here again, let's just quickly whip through fluid page. We've got our title panel. Then we're doing a sidebar layout again, our sidebar panel. But this time in our sidebar panel, we've got a file input component. This, the unique ID for the file input components is upload. The label is upload file. And then there's a keyword argument accept, which takes a essentially a list of names of different file types that will be accepted by the import component. And here I've just set it up just to take CSV files. And there's a few different ways that CSVs can be defined. But all of this is very much covered in the documentation and tells you all the different names that you should use for the different file types that you want to bring in. There's too many for me to go through. So that's it. We're just going to have the file input component in the sidebar panel. Then in the main panel, we're going to have a table output, and that's it. Unique name is going to be data table. Now, our functionality when reading in data. So we need to first of all define our data read-in function. So this function is called myData, and this is a reactive function. And if you remember, the first line that we need to use here is require input $upload. So our upload component is called upload, and we need to say that this function requires input $upload, and it's just, again, a bit of a quirk within Shiny apps. It's how they managed to get it to work. Might change in later versions. We then define the read function, and this is going to use the input. It's going to output to the object df. It's going to read.csv, use the readSeek.csv function, and it's taking the input $upload $data path. Now, this is a standard thing from in Shiny, that we extend the upload object, the upload ID call. So, yep, this is called upload, but we need to get from that object, from this component, specifically what we need is the data path. And we do that by going essentially a $level deeper, and getting the data path attribute of our file upload object. So this is, whereas before there's one attribute that we collect from a slider, which is its value. That's what's passed by default. This time we have to say what it is that we want from our component, and that's the data path. And that will give us our path to the file. And there's just a small transformation just to extract the first column of the data frame, just to make it easier to render in the table as a vector. So that's our data, and then it's returned as we return data from that. So that's a little bit different from the last reactive function that we saw, where it was all, we didn't need to put a return in the function, and we didn't need to require the upload component itself. So just a little bit of a different one, but this is a very standard template for data import in Shiny, and can be used as such. So that's our reactive function that we've got there. And now we can just call that reactive function within our render function here. So we're going to pass out to output to our output object data table, and we're going to pass to that the output of my data and render it as a table. So if I run this, we get this, what will be a familiar data upload component. I can then go in and I will go to, let's get the right example, the import example, and I'll get some example data, CSV data, and we can see there it's been rendered as a data table just in a single column. And it even tells you when it's complete. It's all quite nice and easy there. So there's a few little tips and tricks with using Shiny in this way. And as we mentioned earlier there, that with our input objects, we need to, most of the time, or some of the time, they produce just a single value. But sometimes they produce slightly different outputs, and so you've got to go in and pick which outputs you want, which is where we were looking for the data path in the import component. So little things like single components produce just a single value. A single input object of type string, boolean, integer, or double will just be a single value, and a single value can just be evaluated directly, as we saw previously with the slider. The slider was just producing a single integer value for us. Groups or range components produce a list of values, and they could be of type string, boolean, integer, or double again. But these, where it is a list being returned, they need to be evaluated iteratively. So in some form of a loop or apply function. Okay, so I'm just going to wrap up just with a very small amount of, just a small bit on app deployment. Then I'm going to just leave the, well, I think we'll call it a day after that. But I suggest having, if you're interested in Shiny and Shiny apps, going in, having a look, breaking down the distribution fitting app for yourself, and having a look at different ways that it can be, it might be extended, or different ways different things are working, and just have a bit of an explore on your own. Or you might want to set up a call if a few of you are perhaps really interested in Shiny apps. But so app deployment with Shiny apps ranges from very easy to fairly difficult. So you can run at a web address if you have a web address. They run on GitHub. You can actually embed simple apps within a GitHub page and just host them for free on there. RunGist is a service operated by GitHub, and that again, it can be used for hosting Shiny apps. There is Shiny Apps IO, which has both free and paid options for hosting apps on a standalone web page. And this is the, for for more other people to use it, this is the simplest option for hosting Shiny apps. You get Shiny Server, which there are free and paid options. It requires the use of a Linux server within Shiny Server, so you could have a little bit familiarity with Linux. And you also need your own domain name and to pay for the server space. And Shiny Proxy is similar to Shiny Server, but again, free is a bit of a relative term. They help in some instances. There's just different functionality in there, so it's worth having a look at the options if you're thinking of hosting a Shiny app. But for development purposes, you don't need to be paying anything, and there are options for hosting just for work within your own group and things like that. So I was going to get you to build that distribution fitting app, but it's got a little bit late in the day. If you fancy having a go at building your own, I won't stop you. I think it's if you're going to be doing lots of distribution fitting, it is an incredibly worthwhile task to do. Yeah, it saves just running code over and over again monotonously. It can be quite fun, and a nice way to learn. There's some Shiny resources here. There's some links to the tutorials. Masteringshiny.org is a great website. Here's the main documentation for it from our studio, and an overview of deploying Shiny apps with minimal effort. It's always the best way. Don't get too bogged down in deployment. It's a headache. So I think that brings me to the end there. Got a few minutes just if there are any major questions or anything that anybody'd like to ask? Otherwise, I will release you for 2021 and your HSMA duties. So well done, everybody. There's a lot of training. It's a lot to learn, a lot to be exposed to. So yeah, congratulations.
Thank you, Sean.
You're welcome. You're all very welcome. And yeah, if you've got any questions afterwards, things come up over, I'm on the Slack and things. So yeah, questions afterwards, you get into something next year and are thinking of doing Shiny or anything. So, network analysis, you get into anything like that, welcome to contact me.
Thanks very much, Sean.
Well,
Have a good
Thank you so
Christmas.
good Christmas, everybody.
Yeah.
Merry Christmas, everybody.
Bye.
Merry Christmas all.
Bye.
Bye.
Bye. Take care.